Okay, so I want to introduce this lesson by talking about asymptotes, which I'm sure you guys probably did a lot of work with in pre-calc and probably knew about them for maybe a couple of years before. And the first definitions you probably had were something along the lines of, oh, it's a line that you can get really, really close to, but you'll never touch it. And like no explanation of why, no explanation of where they came from, just kind of that they exist. So asymptotes actually have their definition in calculus, more specifically with limits. So we're going to talk about horizontal asymptotes as well as vertical asymptotes and where they come from and why they're so deeply rooted in the idea of limits. Okay, so first idea that we're going to talk about basically surrounds horizontal asymptotes. And so we define these as finite limits as x approaches positive or negative infinity. So basically, if you plug in large values of x, either negative or positive. And now one note I should make, when I say a tiny number, I mean close to zero. I don't mean like negative a billion. Like that's a negative large number. Tiny numbers close to zero, and then large numbers can be either positive or negative, just to clarify. So if you plug in huge values of x, either positive or negative, and your function approaches something, a finite limit, say it approaches 3, what we end up dealing with are horizontal asymptotes. So let me kind of sum up what this paragraph says here. So infinity, first of all, we're not talking about a real number. It just represents the idea of x getting really large. Like it says here, outgrowing finite bounds. So continuing as far as you can imagine to the right on the x-axis, or continuing as far as you can imagine to the left. So we're talking about what happens as you plug in those very large numbers. So example 1, talking about this function right here, we want to investigate the limits at infinity. Okay, so let's do 2 different limits. So the limit of f of x as x approaches positive infinity, and then we also want to talk about the limit of f of x as x approaches negative infinity. Okay, so take a look at this function right here. If we're plugging in numbers as big as you can imagine, starting with like 1,000, 10,000, 100,000, into the billions, beyond that. If our denominator is getting absolutely gigantic, even bigger than we can possibly imagine, what's going to happen to this fraction is it's going to get smaller and smaller and smaller and smaller. It's headed towards 0. Okay, and then picture the other direction. Say you're going to the left of the x-axis. What's happening as this denominator gets really large, but in a negative direction? Well, you're still approaching 0, but just from the left. Like it'll be a negative teeny tiny number. So this is still approaching 0. So as x gets infinitely large in either a negative or positive direction, we're approaching a finite number of 0, which means 0 is a horizontal asymptote of this function. Let me just show you a sketch, and I'm sure you guys recognize this function. So this graph looks something like this. So you can see as I head off to the right, this is just getting closer and closer and closer to that line y equals 0, but from a positive direction. So it's a positive tiny number. And then as you go off to the left, this graph will just get closer and closer to the line y equals 0, but from a negative direction. So a negative tiny number. Either way, we consider this to be a horizontal asymptote. And it's not because it's a line that you get close to but never touch. It's because our graph has a finite limit as x approaches positive and negative infinity. Okay, so just a quick introduction there. So like I said, we say that this is a horizontal asymptote. So here's your official definition of what a horizontal asymptote is. We say y equals b is a horizontal asymptote if either one or the other is true. If either the limit as x approaches positive infinity ends up being b, or if the limit as x approaches negative infinity ends up being b. Okay, so it could be one or the other, or both. It's actually possible for a graph to have 2 horizontal asymptotes, because you could have one limit as you go towards positive infinity, and then you could have a second different limit as x approaches negative infinity. So it is possible for a graph to have 2, and we'll deal with some functions like that in the future. Okay, so keep that idea in mind. Okay, so example 2. We're going to investigate this a little bit. So we want to look at graphs and tables to find the limit as x approaches positive and negative infinity of this graph right here. Okay, so let's look at a graph first, almost so that we know the answer before we investigate, and then I'll show you a little trick that we could use. So go into your calculator. If you've got the Inspire, either add a new graph page or start an entirely new document. If you've got the 84 or 83, remember your y equals button is right at the top left corner, and you can just type that graph in. So I'm going to open a little fraction template, put an x in the numerator, and then my square root button is right next to the 4, so control square root of x squared plus 1. Okay, here, sorry, I should probably have my keypad up. So the square root is right here. The squared button is also right there. You should have to hit control to get the square root. So hit enter, and my graph looks something like this. So we're going to give a little sketch, and you can also see pretty much exactly what's happening here. As I go off to the right, see how my y value is just approaching 1. It's not going to go any higher than that. It just approaches 1 the bigger my x values get. And then as I go off to negative infinity, my graph is approaching negative 1. So this is one of those rare scenarios where we actually have two horizontal asymptotes. So let me show you a quick sketch just so we've got it in front of us. So it kind of curves along this way, goes up, goes right through the origin, and then curves along this way. So it's got a horizontal asymptote of 1 as well as negative 1. So two different ones here. You could also look at a table if you wanted to, and you can see on here if we hit Control T, it'll open up a table. And you can look, the bigger your numbers get, see how close they're all getting to 1. You just get closer and closer and closer to 1. The farther you go, it's never going to pass it. The bigger your x value gets, the closer it's going to get to 1. And if you headed off in a negative direction, you would see the exact same thing happening there. Okay, so now here's the little trick I want to show you. Let's write these out. The limit as x approaches infinity of f of x, and then the limit as x approaches negative infinity. Okay, so this denominator is super, super, super important. And we're going to get into this a little bit more in the second half of the lesson. But if you're looking just at this part, here's something that is very, very important that I want you guys to know. Kind of off topic, but the square root of x squared, most people think that's x. It's not x. It's the absolute value of x. Okay, so say you plugged in like a 3. 3 squared is 9. Square root of 9 is 3. You get a 3 back in that scenario. But say you plug in a negative 3. If you plug in a negative 3 and then square it, you get 9. And then if you take the square root of 9, you get 3. So it's not actually x. It's the absolute value of x, which you'll see. Let me just prove this to you really quickly. I'll show you on a graph page. If you type in the square root of x squared, see how you get that absolute value function instead. All right, so just a little fun fact there. So this graph, if I plug in really, really, really big values of x, this one, tiny little 1 in the denominator is hardly going to make a difference at all. Say I plug in 1,000,000. 1,000,000 over the square root of 1,000,000 squared plus 1. That one is going to do almost nothing. So this function is actually really, really, really similar to this. Or we say it behaves like this function right here, which has one of two things. Here's what we've got. If we plug in positive numbers, positive 1,000, positive 1,000,000, this looks a lot like 1. The numerator would be positive because I'm plugging in positive numbers. The denominator would be positive because it's an absolute value. So this is going to look a lot like 1. If I'm plugging in negative numbers, this fraction is going to have a negative numerator because I'm plugging in negative numbers, but the denominator is going to be positive because it's an absolute value. So then this would look an awful lot like negative 1. Remember, the bigger x is, the less of an effect that plus 1 is going to have. So that's why as you get farther and farther and farther out, this looks an awful lot like this, which is either positive or negative 1, depending on if you're plugging in positive or negative numbers. Okay, so that's more of an analytical way to look at it, rather than looking at a graph or looking at a table. Because sometimes, and on the AP test this will happen, sometimes you won't have a calculator in front of you, and you'll have to kind of mess around with numbers like I did here. Okay, let's look at a theorem. These are properties that we actually already wrote down. The only difference here is that we have x approaching positive or negative infinity instead of approaching a number, which we called c in the old set of notes. So I'm not going to explain them a ton. I'm just going to write them down. So the limit as x approaches either positive or negative infinity, if I am adding two functions together, I take the limit of the first one and add it to the limit of the second one. Okay, so when I take the limit of the sum of two functions, I get the sum of their two limits. And then the subtraction one works exactly the same. If I have one function minus another function, and I want to combine them as a new function, I just subtract their limits to get the answer. Okay, if I am taking the limit of a product of two functions, if I want to multiply f of x times g of x, again, just like the old property on the last set of notes, I just multiply the two limits together. This one is called scalar multiplication. If I want to take a function and multiply it by a constant, so remember we use k for a constant, I just take the limit and multiply it by that constant. So make sure you guys have that because we do have one more property, which I believe got stuck on, two properties. All right, so we've got division. So you just divide the two limits. Remember, of course, that m can't be 0. We know we're not allowed to divide by 0. And then the very last one that we had, if we take a function and we raise it to a power, let's say n, it's the same as taking the limit and raising it to the power as long as that ends up being a real number. Like you can't take the square root of a negative or something like that. So let's add a little note. As long as the n is real, meaning it's not a complex number or imaginary in any way. Okay, so let's use some properties to find this. So for that one, the first thing that we're going to do is actually a pretty common move, which seems like a weird thing to do. We're going to take this function, it has the same denominator. It's kind of like uncombining common denominators. So we are going to write this function right here. We're going to like uncombine like terms, and we're going to write it as 5x over x plus sine x over x. This is a move that you will end up doing a lot. It's a move that people forget about all the time because we're used to doing this. We're used to going from this side to this side, like, oh, they have the same denominator, I can combine them. We're not used to doing this, but this is often very, very helpful. Okay, so we do this, and you see we can keep simplifying because the x and the x would cancel each other out as long as x isn't 0, and we know it's not because we're approaching infinity. Okay, so we started with this function right here, and we ended up writing it like this. So let's go back into our limit language here. So if we're taking the limit as x approaches infinity of 5, and then plus sine x over x. So this is our function that we're dealing with here. So now we can start to use the properties. One of our properties tells us that if we have the sum of two functions, we can split them up, take two separate limits, like this. So this is easy. This comes from one of our properties. It says if you're taking the limit of just a number, it's always going to be that number. 5 is like a horizontal line. Does not matter what x value you go to, this is always going to be 5. And then plus, now this one should be familiar. Let's flip back to where we had that function, which was a few sections ago. Here it is. Okay, so here's this function, and if you remember what ended up happening is it oscillated a little bit, kind of wiggled around, but it ended up just getting closer and closer and closer to y equals 0. So that graph had a horizontal asymptote. So this right here, and think about it, sine just goes between between -1 and +1, and then if the denominator keeps getting bigger and bigger and bigger, this is going to head right towards 0. Okay, so this limit right here is 0, and so of course 5 plus 0 gives us 5. And I will prove it to you by showing you the graph. So let me open up a new graph for you. Okay, so let's plug in 5x plus the sine of x. Okay, and then just an x in the denominator. Okay, so see that? When you go out, we're kind of hovering around 5, And I can even zoom out a little more just to show you. Okay, so we're going to zoom out, and the farther we go out, the more this is pretty much just going to look like a horizontal line right at 5. So you've got a little bit of oscillating, a little bit of activity that happens there, but the farther you go out, the more it's going to look just like a 5, and the reason that is because this piece looks a lot like 0, and then I just tack a 5 onto it. Okay, so we're going to stop at the horizontal asymptotes for now, and then in the second half we will talk about vertical asymptotes.